Good evening, students. Today we will discuss few consequences of the postulate that we have discussed so far. Well, today we will mostly discuss three aspects. One is the first aspect is the time-independent equation and the derivation of the time-independent Schrodinger equation. The second one is that the introduction of a stationary wave and stationary state, and why we call it as a stationary state, and what happens to the probability density, and also what happens to the expectation value of a system. These are the three things that we will discuss. And the first and foremost thing is that I will try to introduce what is standing wave. I'm sure that most of you are actually studied what is a standing wave and what are standing waves. And as we have seen that, suppose you just imagine you have a string, and the string is fixed to two fixed points. Okay? Like in this diagram, you can see a string is actually fixed two strings. Okay, when you disturb the string, then it executes oscillations, and the oscillations are waves, and these waves what we call it as the standing waves. So it's a very simple explanation of or illustration of standing waves, and you know that you will have a zero node, and you have a node and a two node, three node, and etc. So we will have different varieties of nodes and anti-nodes will be there accordingly. And what we are interested in is the standing wave patterns in quantum mechanics. So similar to the classical physics, of course, the frequency of the frequency of the oscillations can be estimated, and the derivation, all these things are actually as a part of physics. You might have studied, or at least you might have come across the standing waves. Okay, our standing waves are not very so different. I think you might have seen the sounds that are coming out from a sitar or a violin. All those things are actually standing wave patterns, right? So similar to those standing wave waves, in quantum mechanics we do have standing waves. Okay, quantum systems also, like quantum particles, exhibit the standing wave patterns similar to that of standing waves of a string, or in general standing waves in classical physics. Okay, and these analogous of standing waves in quantum mechanics, what we call as a stationary states. Okay, so stationary states are not so different from the standing waves. These are actually analogous of the standing waves. But when we talk about the quantum systems, we use a special notation kind of thing. And in fact, some people in a vague sense, even the standing waves are also called as the stationary waves. Okay, so in that way also you can remember, but usual convention that the quantum systems, when they are executing some kind of wave behavior, then normally those waves what we call as stationary waves. Okay, and these stationary states of the standing waves of a quantum system can be observed only under certain conditions, not every time. Not every time. Okay, like string, when it is fixed to 2 points, when you disturb it, automatically it makes the waves, right? But unlike that, such a simple case, the quantum systems do not exhibit the stationary states. They only exhibit under a special condition. The special condition is that the potential of the system, if you are imagining or if you are denoting the potential of the system, is V of x, is time independent, then in that situation, the quantum system will actually exhibit the stationary states. Okay, so if the potential of the system, what I mean is the quantum system, the potential, if the potential of the system, quantum system is actually time, if it is a time independent, then there can be states which are actually referred to as the stationary states. Okay, so it is under a special condition they are actually observed. Now, if I say the potential of a quantum system is not is a basically a time independent, then how do we actually imagine or picturize such a situation? Just imagine, as I told you, as the time passes, any quantum, any object, any moving object, as time passes, basically it changes, it evolves with the time. Any quantum system, basically, it evolves with the time. But there are situations where where the potential energy they do evolve, but then the potential keeping the potential energy remains the same initially and then after certain time. So those are the systems that we are going to describe or discuss about it. But let me tell you, are these things are actually really there? Yes, definitely. We do have the systems where the potential of the system is actually constant or independent of time. We do have as quantum systems where the potential of the system is actually changing with time. So both quantum systems are available, and the best example for time dependent system and the system where the potential energy is changing with the time. I can give an example for this. Just imagine, you have a radiation, and the radiation basically interacting with the matter, and the interaction of radiation with matter, what we is basically a subject of spectroscopy. So in spectroscopy, when you are describing the spectroscopy, which is the subject of light matter interaction, especially the laser light interaction with the matter, in such a situation, the interaction is basically is a time dependent. Therefore, the potential actually changes with time. Okay, but there are other systems where, especially, we come up with the potential confined, particle confined to one-dimensional blocks, three-dimensional blocks, simple harmonic oscillators. So these are the system where the potential remain constant through the observation time. Therefore, we have systems where the potential of the quantum systems will be changing, and we do have quantum systems where the potential energy is not changing. Therefore, let me show you how actually this potential is changing with the time and potential is not changing with the time. Suppose you have some system, let's say on the left hand side, and whose as per the postulate that any system that we have, it can be denoted with a psi, and mathematical, it can be expressed in terms of a state function, wave function. And usually what happens with the time, it changes, may increase or decrease or something will happen, right? So after time t, then a certain time t, then it basically is going to change to a different thing. So you can just imagine this is the potential of a system, and which is basically is this much, but later on after some time, basically it is changing. Now, the time independent system is something that it is shown in this cartoon diagram. You can see here that before and after the time, the potential is actually is not changing. Okay, the wave function is not changing, the potential is actually changing. So these are the simple illustrations or simple diagrams to understand pictorially. Of course, they're not very accurate illustrations, but to give a qualitative picture, just I have drawn these two things. Well, let us consider a one-dimensional system which is basically evolving with time. And the time-dependent Schrodinger wave equation is given by IH cross dou by dou t psi of x comma t is equal to there is a kinetic energy operator and then the potential energy operator, which depends upon the position and as well as the time. Okay, and of course it is multiplied by the operator h, the Hamiltonian multiplied by the wave function. It depends upon the time and position. Now, what I'm saying that if the system is not changing with the potential energy, V of x is actually constant with respect to time. Therefore, instead of writing v of x comma t, then we can only write only v of x, right? Because the system potential is not changing. Okay, and the remaining in the time dependent Schrodinger equation, everything same. But this is a special case where the potential of the system is not changing, therefore appropriate changes need to be made. Now having this, then what is the thing that we have to do? And if you look at this particular equation, this is actually partial differential equation with respect to two variables, that is x and t. Right? Do you agree or not? This is a partial differential equation with respect to two variables, that is x and t. So how do we basically solve this equation? Have you come across in your mathematics in the early classes how to deal the partial differential equations when you have two variables?
By variable separation.
Yeah, separation of variables as variable separation. So this method is also referred to as a divide and conquer method. This method is also referred to as a divide and conquer method. What we do, we assume the total function as the product of two functions, and then we basically substitute that assumption, and then we try to separate two exclusive equations, and once we have the exclusive equations, then we can actually solve the equation, and ultimately when you want to have the complete wave function, then you can again substitute back from the solutions what you get, and then you will have the complete wave function. Okay, so that is the complete picture. So it will be clear as I proceed further, but ultimately what you can accept at this moment is that there is a method what is referred to as the divide and conquer method, or the separation of variables method. In this method, we make a substitution. The total function can be thought of a product of two functions, in which one function exclusively depends upon one variable and the other function exclusively depends upon the other variable. Then when you multiply these two, then you will get the complete wave function. So that is the assumption that we make it. So coming to our problem, we have a partial differential equation which depends upon x and t. X is the position coordinate, t is the time coordinate. Now what I am going to assume is that the total wave function capital psi, which depends upon x and t variables, may be thought of the product of small psi of x, capital T of t. Okay, what I mentioned previously, I'm assuming my total function is the product of two wave functions, where one function exclusively depends upon one variable and the other function depends upon the other variable. Okay, so that's how I have I am going to make the substitution, and then let's see what happens. So when I make the substitution, the time dependent Schrodinger equation is going to modify like this. You can see here from the previous equation, what I did in this equation, I just substituted wherever there is a capital psi of x comma t is there I made a substitution. I am substituting with the psi of x, small psi of x, capital T of t, right? And then rest of the things I left it as such. I am not going to do anything at this stage. Then what I do next thing is this. As you can see here, what is this? This is a partial differentiation. Partial differentiation. You have two functions. One is psi of x, the other one is t of t. That means this function depends upon t variable. This function depends upon x variable. Now with regard to the differentiation, the partial differentiation is only with regard to t, that is time. Then what will happen to psi of x? Will it make any change?
It is considered as a constant.
Yes, exactly. So with regard to the partial differentiation with regard to time, The psi of x doesn't change. It is constant. It is assumed as a constant. Therefore, this actually you can move outside. This actually you can move outside. That is what precisely I am going to do. And similarly, similarly, another thing which I have done on the right hand side on the above equation. You see here, okay, there is a linear summation of the kinetic energy operator and the potential energy operator. You can see here both depends upon x variable, not t variable. Do you notice here? So there is a h cross square by 2m. This is a constant, right? And there is a partial differentiation 2 times, okay, but with respect to x. And here v of x. Okay, so when you are taking this product inside, basically this comes here and this also comes here, right? This also comes here. But here, what you notice here is that this is a partial differentiation only with regard to x. Therefore, with regard to t, it is constant. Therefore, what I am doing, this t of t, I will write outside the this brackets. Okay, I hope that everybody is following this step. So this partial differential here, it is with respect to t. Therefore, psi of x I have written outside, and here the partial differentiation only with regard to x. Therefore, t of t I have written outside. That's all. Now what I'm going to do, I'm going to divide the entire function with psi of x and t of t. The entire equation, what I'm going to do, I'm going to basically divide with small psi of x, capital T of t. Right? When I do that, what I get outside on the left hand side is this. On the left hand side, okay, I'm dividing, and right hand side is also I'm dividing. When I'm dividing, then naturally here psi of x and small psi of x, both small psi of x get cancelled each other, and on the right hand side both t of t, numerator and denominator, get cancelled each other. So essentially you are going to have an equation like this: 1 over t of t, I h cross dou by dou t t of t, which is equal to 1 over psi of x multiplied by the Hamiltonian operator multiplied by psi of x. Is it clear? As of now, is it clear to you?
Yes, sir.
Yes, sir.
Okay. So once you understood, you try to understand the physical meaning of this equation. On the left hand side, you can see it is 1 over t of t, I h cross dou by dou t t of t. That means there is no x variable, isn't it? Similarly, on the right hand side, you don't have the t variable, right? You have on the left hand side t of t function, and right hand side x function. Let me denote briefly in this fashion. You have an equation, okay, you have a function which actually depends upon t. There is another function on the right hand side which actually depends upon x variable. Okay, this left hand side you imagine as a one function, and right hand side you imagine as another function which depends upon the another variable. Now, what is there in between? What is there in between? What is this? There is a equality, right? Okay, there is a equality. This f of t is equal to g of x. F of t is equal to g of x. That means both functions are equal. Is it acceptable? If it is acceptable, under which condition it is acceptable? In mathematics, if two functions are said to be equal, and only when if they are actually equal to some other constant independently, right? This only happens, this is one variable, one function, and another function depends upon another variable. Now I am saying both are equal. When it happens in mathematics, this happens, this function f of t, on the left hand side function, which depends upon one variable, it has to be equivalent to some constant. Similarly, on the right hand side, I have another function which depends upon x variable, which must be equal to some constant. Of course, it is not some constant, the same constant as the left hand side function, which is equal to the constant. So essentially what I mean is that this only true, both functions actually equal to one constant. Otherwise, that above equality cannot be satisfied. Do you understand this logic? The two functions independently must be equal to one constant. Only then the above equality can be satisfied. Otherwise, it is not possible. Okay. Now, therefore, so this is what exactly is the meaning of the variable separable method, or divide and conquer. Yeah? When you can't handle two person who are really who are really very close to each other, then what you do, you try to divide and rule, right? The Britishers rules, divide and rule. It is like this. So when you can't handle the mathematical equation, which actually having more than two or more than two variables, then the best method is that you divide and conquer, right? Or variable separable method. So this is the method. So initially we have a function. That function we have assumed as the product of two separate function, in which one depends upon one variable, the other depends upon one. The product may give you the total function. So by assuming that, what we made so far is that we made a substitution and we try to here and there make small little bit of changes and rearrangements according to the equation. And what ultimately we got is the two different equations. And these two different equations are much easier to basically handle. Again, you can see here, this is a partial differential equation and this is another partial differential equation, exclusively depend upon x variable. Now, I will pose one question to all of you. If we started with the condition that if the potential energy depends upon time, is it possible to do all this process? I repeat the question. Suppose if the potential energy depends upon the time variable, is it possible to do this process? This process means the divide and conquer method or the variable separable method. Is it possible?
No, no, sir.
Definitely it is not possible. So that is why we started with that kind of clause or condition, right? Now, having understood having obtained two separate partial differential equation, now what is the thing that we wanted to do? Ultimately, our aim is to find out what is the capital psi of x comma t. What is the capital psi x comma t? Now, the capital psi x comma t, we thought of the product of two functions. Okay. Now, we got two differential equations. Now, if you are able to solve this thing, okay, if you want to get t of t, then you have to solve this. And if you want to obtain what is psi of x, then this equation has to be solved. And if you are able to get what is this, what is psi of x and what is t of t, then the product of those things can be the solution of the capital psi of t, right? Which is actually the solution of the time dependent Schrodinger wave equation, isn't it? That is what I am trying to do. So, having obtained two equations, we will try to first solve the capital P of t. That means we have to obtain, consider the first equation. That is 1 over capital T of t, IH cross dou by dou t, T of t, which is equal to a constant, that is for the sake of notation, I am taking E because ultimately it is the energy that is going to come up, because the Hamiltonian is basically the total energy. Therefore, I'm just going to going in the direction. So let me take that constant as E is a constant. Now to get the T of t, one has to solve this partial differential equation. So what I do first and foremost thing is that this partial differential equation notation is actually meaningless. Why? Because here on the right hand side of this notation only I have T of t. There is no other thing. Therefore, I can simply write down a simple derivative sign instead of using the partial differentiation. I can continue writing partial differential notation only when I have more than one variable. But I have only one variable. That variable is basically time variable. Therefore, it doesn't make any sense in writing that partial differentiation. Therefore, I will switch over to d of t. Okay, so 1 over t of t h cross d by dt. Okay, of t of t is equal to e. Now what I can do in the next equation, next step, that I can actually switch, I can take this denominator t of t to this right hand side. Okay, so and I can simply do a simple kind of mathematics rearrangements, and then I can obtain this type of equation. Okay, 1 over t of t. 1 over t of t is nothing but basically d ln of t of t, and dt is as removed. 1 over t, instead of writing 1 over t, what I am writing d, okay, d is there, is ln t of t and dt. Okay. So IH cross is a constant is a constant, right? So d ln of t I have written, and I have removed this 1 over t. I hope that you are following. Now what I do now, next step is that, okay, I have this IH cross d ln of t of t divided by dt is equal to e. Now dt I can take the other direction. So this is the denominator. So when you take outside the other side of the equality, then it becomes et. Similarly, what I do, there is IH cross. This IH cross I will take to the other direction, other side of the equation. Then it becomes basically denominator. So essentially, it is going to be this type of equation. And then what I do, I am going to apply I am going to integrate it. I'm going to integrate it. Ultimately, I'm going to integrate it. This is what I have done here. You can notice here that integral d ln t of t. Okay. Initially, from here to here, I'm just straight away writing. After there is a next step. Okay. From there to here, that is the next step. So basically, d ln t of t is equal to v by ih cross. Okay. This dt, I said that earlier, I am going to take this direction. Okay, and this I will move to this direction. Okay. This is the way it is. Now, having shuffled or rearranged that particular equation, then you just apply integration of both sides. That is what I have done in this time. Okay, once you have done this, okay, so there is integration and differentiation, both cancel out, and ln t of t is equal to et by ih cross plus c1, where c1 is the integration constant. Then further, we can actually proceed further, and then you can write down, instead of writing ln t of t, I can also write down equally. Ln you can move to the other direction. Okay. To remove ln, what you can do, t of t is equal to e to the power it by ih cross plus c1. I hope that this convention or the conversion, I'm sure that most of you know it. So the conversion between the ln and exponential function is known to all of us. Therefore, there is nothing can be discussed, nothing is required to discuss here. So instead of writing ln t of t, you can simply write t of t, because why I'm writing, because this is t of t is something that we wanted. So t of t is equal to e to the power et divided by ih cross plus c1. Right? Now what I'm going to do, I'm going to, there is this equation is nothing but e to the power a plus b. This is of the form e to the power a plus b. E to the power a plus b. This can be very much This you can write it like e to the power. Yeah. This you can write it like e to the power a multiplied by e to the power, which one, e to the power a plus e to the a plus b can be written as e to the power a into e to the power b. So that is what I have written here in this part. Okay, so e to the power c1. What is this? Exponential, and c1 is the constant. Therefore, it is basically a constant. That constant I'm replacing with some, denoting with a capital. Now again, just for the sake of convenience, I'm writing, instead of writing I in the denominator, I just wanted to have it in the numerator. So what I did is this. So I have 1 over I. So 1 over I, what I can do, 1 means minus I multiplied by minus I, isn't it? Divided by I. Is that okay? I square is minus 1. I square is minus 1, right? So minus minus 1. So then you can simply cut down these two things, and then you can simply write down 1 minus over there. Okay, so therefore this equation actually T of t is nothing but a into e to the power it divided by h cross. It divided by h cross. Please note down this minus et divided by h cross is there, e to the power. It is in the e raised to. Okay, it is not, it is not like this. So this is wrong. So there are many cases where students are confusing and writing like this. So this is not the case. It is e to the power. So e to the power minus I h cross. Sorry, et divided by h cross. It is there. Okay, so that you please note down the difference. Now we have obtained the solution for T of t, isn't it? This is what we wanted. But this is not enough, because we want to get the complete solution. That means we have to get this, what is the solution of psi of x. To get the solution of psi of x, we have to take the second equation. The second equation is exclusively, I have just rearranged the equation. Actually, if you see, this is 1 over psi of x actually. 1 over psi of x was there. Then what I did was actually I have moved psi of x to the other direction. Okay, that's all I have done. It's a small rearrangement I have done. Now what you can notice here, you see that what is this? What is this? On the left hand side, this component is what? What do you call this component?
Hamiltonian.
Yes, exactly. So this is a Hamiltonian.
Hamiltonian.
Correct, correct. So this is a Hamiltonian, and when it is operating some function psi of x, and you are getting back your function, right? Please remember that e is a constant, right? Isn't it? What do you call this relation?
Eigenvalue equation.
Correct. So you are basically getting a eigenvalue relation, right? Now you remember one statement I made, very important statement. I also mentioned that statement as important. For a given Hamilton, for a given operator, there can be several eigenfunctions, right? This is basically a eigen relation. What you see on there. Okay. Now the H is the total energy operator. When it is operating on one function, you are getting one constant, and multiplying then the same function you are getting. That means basically this is an eigen relation. and the Hamiltonian is a operator, and the operator, since it is an operator, for a given operator there can be several eigen functions. There can be several eigen functions. Corresponding to each eigen function, there can be specific eigen values or eigen values, right? So let me assume. So this is that relation, and let us assume that psi 1, psi 1 of x, psi 2 of x, psi 3 of x, and so on, psi n of x are the eigen functions of the operator, that is the Hamiltonian. Okay, so if you are why you are assuming this? Because for a given operator there can be several eigen functions. Okay, so now based on that I am assuming this, and then corresponding to each eigen function there can be eigen values. I assume that e1, e2, e3, and e4. Okay, so when psi n of when the Hamiltonian is operating on this psi 4 of x, then I will get a e4 is an eigenvalue. When when the operator is operating upon the Hamiltonian operator is operating upon the uh, uh, nth eigen function, then I will get nth eigenvalue, right? So that means you got the equation what actually you are looking at. What is the equation? H psi n of x is equal to e n of psi of x. Of course, I forgot. Please note down. Here there will be n. Please note down the correction. Here there will be n. So somehow I missed out while drawing. Please note down this. Okay, so this is what h psi is equal to e psi, isn't it? This is nothing but the h psi is equal to e psi. What is h? What is h? H is the Hamiltonian operator, which is nothing but the total energy operator, where kinetic energy operator plus potential energy operator will be linearly coupled with each other, right? So this is what is the derivation of the time uh, independent Schrodinger wave equation. Why this is said to be time independent? As you can notice here, then there is no time value, time variable. Remember, what is the Hamiltonian? Hamiltonian is only having the x variable. Usually, most all the variables will have any of the operator that you may think will not have any time variable. That is for sure. But here you started with a Hamiltonian, and this Hamiltonian it doesn't have any t variable. It doesn't have any time variable. It's already only it is having only x variable, right? And wave function also depends upon x variable. It doesn't depend upon t variable. Therefore, this particular equation, what we refer to as the time independent Schrodinger wave equation. Time independent Schrodinger wave equation. Okay, now this equation, what is the psi of x actually? What we have done actually, see, we wanted to find out what is psi of x, and we already found what is psi of x. The psi of x is nothing but the eigenvalue, eigenfunction of the Hamiltonian operator. Psi of x is nothing but the eigenfunction of the Hamiltonian operator, isn't it? Are you following this logic? Any doubt here? Psi of x is nothing but the eigenfunction of the operator. What is the operator? In this case, it is only Hamiltonian operator. Okay, so we found our solution of psi of x. So our psi of x is nothing but psi n of x. Is nothing but psi n of x. That's all. So we got the time independent wave equation in the process. But this is not done. Why? Because you remember our total wave function, what we started is actually is the product of two functions. What is that? Psi of x and t of t. Right? Now t of t already we obtained. What is t of t? We already obtained. Well, you can substitute what is psi of x and what is t of t to obtain the total wave function. Okay. Now psi of x is nothing but sin of x. What is sin of x? Sin of x is nothing but the eigenfunction of the time dependent, time independent Schrodinger wave equation. So this equation, what we call it as a time independent Schrodinger wave equation. So it is the solution. It is the solution. Sin of x is nothing but the solution of the time independent Schrodinger wave equation. To obtain the sin of x, what you have to do? Actually, you have to solve this equation. So this has a lot of importance and great significance in quantum chemistry. So if you are able to solve the time independent Schrodinger wave equation, you will be able to get sin of x. Okay, once you obtain sin of x, you get the total wave function, which actually changes, which actually depends upon the position as well as the time variables. Then you multiply with the t of t. What is t of t? T of t already we obtained. It is nothing but a constant multiplied by e raised to minus it divided by h cross. Right? Minus IH cross. Now, what we normally do, this A, what is A? A is introduced as a constant. A is introduced as a constant, right? Now, this A I will remove. Why? Because what is this? This is the eigen function. Normally, the functions or the mathematical eigenfunction or the state function of the systems, whatever we may think of or we may take the wave function, those wave functions will be normalized. Therefore, this is not necessary to write again another constant. So anyway, the wave functions are going to be, we are going to ensure the normalization, say normalization condition. Right? This is something that we already discussed as a part of, once you have the state function has to fulfill three conditions. It has to be normalized, okay, ensure that it has to be single valued, okay, and it should be a continuous wave function, and it should be satisfy the normalization constant, normalization condition. Only then such a state function will be taken as the state function. Any function is thought of as state function or wave function for a quantum system only when it is met three conditions. One is normalization condition, the other one is the single valued condition, and also the continuity condition. Therefore, this A we need not to write again. So therefore, we have removed. And then similarly, and then the exponential function we have, and exponential function, it is IE t divided by h cross. So this is the total function, and since we have nth eigenfunction and the energy, corresponding energy will be, let me make a differentiation. So when nth eigenfunction, when the operator, Hamiltonian operator is operating upon the, in this particular case, this is the time independent Schrodinger wave equation. When the Hamiltonian is operating upon the nth eigenfunction, we are getting nth eigenvalue. Therefore, assuming that here I am just making a small substitution or small notation change. Instead of writing here, since I have the nth eigenfunction, it is appropriate to write here. I should differentiate that energy, because for a given state, for a given stationary state, it will have certain amount of energy. And if you have a different state, it will have a different energy. Therefore, it is better to differentiate those states. So all the states may not have the same energy. Of course, we do have the degenerate and non-degeneracy that we will discuss, but it is appropriate since the function what we are discussing here is the nth eigenfunction. It is appropriate to differentiate the energy eigenvalue also. Therefore, the total wave function capital psi of x comma t is none other than it is small psi n of x multiplied by e to the power I En of t divided out by h cross. Okay, please remember that to obtain psi n of x, which is the eigenfunction, then what you have to do, you have to basically solve the time independent Schrodinger equation. That is this equation. Okay, I already mentioned that it has to be corrected a little bit. So this is called time independent Schrodinger wave equation. Time independent Schrodinger wave equation. So any system that you may think of, if its potential energy is not changing with the time, in other words, if the potential energy is constant, then what you can do, you need not to solve the time dependent Schrodinger wave equation. Instead, it is enough if you can solve time independent Schrodinger wave equation. Once you solve the time independent Schrodinger wave equation, then you will obtain psi n of x, the wave function, that you can multiply with this factor, the time exponential function. So this is the function that actually takes care of the time evolution of the function, of this time evolution of the system. Okay, to obtain the total wave function, then you just you solve the time independent Schrodinger wave equation, and you will get the wave function, and that function you multiply it with the time function, that is e to the power I n t divided by h cross, which essentially gives you the total wave function. Okay, that function, that is what function? This function is ensured that it will satisfy time dependent Schrodinger wave equation. So this function will definitely satisfy time dependent Schrodinger wave equation. Okay, so you got the answer, or you got the logic, all of you. Do you have any questions until now? Just ask, otherwise I will proceed.
Sir, can you please explain once more?
Which concept?
This time dependent time.
Yeah, up to
The last
yeah. What I'm saying, the last portion, what I'm saying. See, we initially we started with the total wave function is the product of two wave functions, and we obtained two equations, and the time equation we solved, and we got some value, and the second psi of x also we got a solution. That is nothing but it is the solution of the time independent Schrodinger wave equation. We don't know what it is. As of now, we don't know anything. What we have to do, if you know the system, then we can write down the Schrodinger time independent Schrodinger wave equation, and then you solve the equation, and we will get the what is the wave function. That wave function you have to multiply with the time t. Okay, you have to multiply with the time factor. This is the time factor, and this is the spatial factor. So this time factor, this wave function you will be getting if you solve this equation. If you solve this equation, you will get sin of x, and if you get sin of x, then that you multiply with the time factor to obtain the total wave function. Okay, once you have the total wave function, this total wave function is ensured, and it will definitely satisfies the time dependent Schrodinger wave equation. What is time dependent Schrodinger wave equation? Time dependent Schrodinger wave equation will have two variables. Please remember IH cross, okay, and there is a Hamiltonian on the right hand side and plus V of x comma t. The problem is that if the potential energy is basically uh, having two variables, then it will be very difficult to handle those equations, difficult to find the solutions. Therefore, there is an indirect method is evolved. What is being suggested is that there are systems where the uh, potential energy is constant. If the potential energy is constant, then we need not to solve time-dependent Schrodinger wave equation of a system. To get the solution, what is recommended is that, first of all, we have to solve the time-independent Schrodinger wave equation, which is nothing but h psi n of x is equal to en psi n of x. That is the time-independent Schrodinger wave equation. Okay, once you solve this equation, then you will obtain psi n of x. Once you obtain psi n of x, that psi n of x you have to multiply with the t of t. Oh, sorry, the time factor. This is the function, actually time factor, which describes the time evolution of the function, time evolution of the system. Okay. Now this total product will is nothing but the capital psi of x comma t. Okay, and the total thing will actually satisfy the time dependent Schrodinger wave equation. Am I right? Is it clear to you?
Yes, sir, it's clear now.
Okay. Now, having found the solution, now the total, what is the solution? What I'm saying, the solution, this is nothing but a solution. Psi of x comma t is equal to psi n of x multiplied by e to the power I e n of t by h cross is a solution. Is a solution of time dependent Schrodinger wave equation. Only if you are talking about, if you are solving only this equation, then you will obtain only the spatial wave function, but not time. It doesn't describe the time evolution of the system. Okay, so that is the point I am trying to say. Now, having understood the solution of time dependent Schrodinger wave equation, now we will see few two properties, not many properties. One property is the probability density of a stationary state. Probability density. Okay, I told you that in, similar to standing waves, in quantum mechanics or the quantum systems will have a stationary states. Okay, and why these are said to be stationary? The answer actually is, I'm going to disclose after a small derivation. You can just imagine a system is actually moving in one dimension, one direction, right? The system is evolving, basically, the system is actually evolving with the time, and the system is actually confined to one dimension. That is, for the sake of convenience, let us confine ourselves to a system is actually traveling in one particular direction, that is x direction. Okay, if you have such a system, then what is the wave function? The wave function is nothing but the capital psi of x comma t, isn't it? The wave function of such a system is nothing but the capital psi of x comma t. Now, what I wanted to evaluate is the probability density. You remember the probability density is nothing but the psi star psi of psi star psi dx, right? Integral psi star psi dx, right? That is the probability density. Now, the probability, you can actually do a small math. Now, what I have done here is this. So, capital psi of x comma t, as per our previous definition, it is nothing but the psi n of x multiplied by e to the power I e n of t by h cos. Please note down that again I have missed out the notation en. It has to be e suffix n. So please note down. I think when I share the slides, this modification I shall send it to you. But for the time being, please note down everywhere you will have a n. This is n. E suffix n. This I forgot to mention here. So everywhere it is n. So what I am trying to do, that the probability density of such a system. What is a system? The system is actually traveling. The system is moving in one particular direction, that is x direction, and in between a small interval, that is dx interval. I just wanted to calculate what is the probability density. And the probability density is nothing but the psi star psi the tau integral, right? So when I'm trying to evaluate, then the capital psi of x comma t, as per the previous discussion, it is nothing but the psi n of x, psi of x multiplied by t of t, and psi of x is nothing but the psi n of x multiplied by e to the power minus I n t by h cos. Right? That substitution basically I'm trying to make. When I make this, okay, here, when I make this substitution, okay, I have psi n of star x, psi n of star x. I hope that you know what do you mean by psi n of star x. So the star indicates the complex conjugate. Star indicates the complex conjugate. The wave function psi n of x, we don't know what it is. Therefore, still we should continue the star notation in the next step. But here there is a e to the power minus I e n t by h cross, and it's a complex conjugate. What is a complex conjugate of this? Okay, there is a negative. There is a minus I. The complex conjugate of minus I is nothing but the plus I. So that substitution I made here. Then multiplied by this function. Okay, this function. Now you can see here there are. This is only just a product, right? It is all a product. Psi n star x e to the power I n t by h cross multiplied by sine of x e to the power of minus a n t by h cross dx. So this is all a product, so I can just interchange their positions here and there as per my convenience. So I will, if I do that, ultimately what I will get is this. So I have two exponential factors, that is these two factors. These two are the exponential thing. There is a e to the power I e n t by h cross and e to the power minus I e n t by h cross. So what is the answer? The answer is 1. E to the power a multiplied by e to the power minus a. What is the answer? The answer is e to the power a minus a. Therefore, e to the power a minus a means e to the power 0. E to the power 0 means anything to the power 0 means 1. So based on that, this factor becomes 1. Therefore, essentially what I obtain is this integral psi n star x multiplied by psi n of x dx. Okay, so this is the probability density. This is the probability density. Now, if you evaluate this integral, do you get any time constant or time variable after solving this integral? And of course, definitely not, because the wave function is actually x variable. It doesn't have any time variable. Okay, therefore, basically, it is a time independent. What is time independent? The probability density doesn't depend upon the time. It is only depend upon x variable as per this integral. That means it is independent of time. Since the probability independent of time, then these actually states are said to be stationary. These states are said to be stationary. That means they do not change. The probability do not change with time. Please note down, please note down, the system is evolving with time. That is there, that is there. But its a probability doesn't change with time. When this happens on the system, when the system potential is not changing with the time, then there can be states what are referred to as the stationary state. I mentioned this statement when I began this class. The system is said to be stationary because its probability doesn't change with the time. Why? Because there is a small derivation I showed here. In this integral, if you look at carefully, it doesn't have any time variable. Therefore, I claim that the probability of a system whose potential energy is not changing with the time is going to be time independent. It doesn't change. Right? Therefore, I call such a state as a stationary. It is not changing. Stationary means, I know the meaning of the stationary. It doesn't change with the time. Okay. Similarly, we can also evaluate the expectation value of such a system whose potential energy is not changing with the time. And the expectation value, as we all know, okay, psi star, integral psi star, the operator multiplied by psi dx divided by integral psi star psi dx. So this is the basic definition. Okay, as our system is changing with the time, therefore we have to have the total wave function, which is actually is the product of two wave function, that is the psi of x and t of t. Okay, I just made that substitution initially. Now I am going to basically make a few more substitutions. Here, you just look at this. What is this? The denominator in this equation. What is the numerator? What is the denominator? The denominator just now we evaluated. This is the probability. Integral psi star psi dx is the probability, right? This probability we just showed already. It doesn't change with time, and in fact, it is nothing but this quantity. Just go back and see. What is this? Integral capital psi star x comma t psi x comma t dx. This is the probability. This probability is basically is nothing but the psi n of x multiplied by psi n of x comma x multiplied by dx, right? So it doesn't have any time thing. Now what I'm saying, the denominator of the expectation value is nothing but this. Is going to be this. It is only x variable. It doesn't change. I'm coming to the numerator part. Again, you can do the same trick. You can do the same trick as previously done. Okay, so you just write down what is t of t, and also you write down what is psi of x. So psi of x is nothing but the psi n of x. Okay, and wherever there is a complex conjugate, you can take that complex conjugate and then apply. Okay, so here psi of x star is there. Therefore, I have written psi n of x, psi n star x. I have written, and then t of t complex conjugate. So I have written this, and then there is an operator, and then instead of writing psi of x, I need to replace psi n of x, and this t of t again I have to write down e to the power I en of t. So that is there. Now again the same thing. As I told you earlier, generally the operators do not have any time component. Generally that is the case. Therefore, even though it is an operator, actually we are not supposed to simply move anything which is on the right hand side just like that. Okay, the operator, it can be a simple derivation or the second derivation, right, with respect to the position, but not with respect to time. We don't have any operator which depends upon time. So therefore, what I can do in a simple expression, this is a time thing, e to the power minus I et by h cross. This is the time factor. Therefore, I can simply move to the other direction. Why? Because the operator may not generally do not contain any time thing. Therefore, I can freely move the this time component outside. But certainly, I cannot move sin of x. Why? Because operators do have the x variable. This I cannot move. This is not possible to move this direction. But this I can move based on the assumption that based on the normal situation or the fact that the operators do not contain any time factor. Okay, so when I do that again, this is actually having e to the power the complex conjugate of minus I is going to be plus I. Okay, and then basically e to the power of minus a. Okay, when I know that, this is what happens, and both basically gets cancel each other. These two actually cancel each other, and essentially we are going to get what? The expectation value will be integral sin of star x operator a sin of x dx divided by integral sin of x dx. That is the factor. As you can again see here that there is no time thing. It is only the position variable. It doesn't contain any time thing. Okay, so this is another reason that why it is said to be a stationary. If you have a quantum system whose potential energy is not changing with respect to time, then we have already shown that the probability doesn't change. And similarly now, with this equation, it is understood that its a potential energy, its expectation value doesn't change with respect to time. It remains the same. That means when you are trying to calculate the expectation value, which is physically is nothing but the average of many experiments, right? Expectation value or the average value is nothing but the average of many values. These are actually in quantum mechanics, as per the postulate number 3, we need not to do that. Simply we can calculate the expectation value, right? So that expectation value under these conditions, it is going to be independent, time independent. It doesn't depend upon time. Whether you calculate now or whether you calculate after a few years, it doesn't matter. It remains the same. It is constant. Since the probability and the expectation values of the quantum systems whose potential energy is not changing with time, we call such a states as the stationary states. Such a energy states, what we call it as an energy state, what we call it as the stationary states. With this, I complete my discussion today. If you have any queries, you can ask me. Otherwise, we can stop the class. Thank you for listening.